Hello everyone, welcome to another Kinetic tutoring episode. Today we're looking at 2017 AP Physics C Mechanics Practice Test question number 2, FRQ number 2. So let's just get straight into the problem. A cart of mass M is on a level horizontal track. The cart is attached to one end of an ideal spring. The other end of the spring is attached to a vertical support. The spring has a spring constant K. The cart is pulled to the right and stretching the spring a distance d, as shown above, and released from rest at time t is 0. The cart spring system begins to oscillate, and the point x of the cart as a function of time t is given by the equation x of t is equal to d cosine omega t, where x is in meters, omega is in radians per second, and t is in seconds. Assume the mass of the cart's wheels to be negligible. Derive an equation for the velocity of the cart v as a function of time t. Alright guys, part A is pretty straightforward. We know that the velocity of a particle is simply going to be the derivative of its position function with respect to t. So d dt of d cosine omega t. We know that the derivative of cosine is negative sine, so we get negative d sine omega t. But we have to keep in mind that we need to multiply that by the derivative of the inside, which is omega, and here will be your final answer. This is your velocity function. I'll write it a little bit better over here. And now here it's asking us to sketch a graph of the velocity of the cart as a function of time t for 2 complete oscillations. On the graph, t represents time for one complete oscillation, expressed label asymptotes, maxima or minima with algebraic expressions as appropriate. Alright guys, so when we take a look at the velocity function, we see here that it is a sine graph, but it's a negative sine graph. So it's going to be going down, start at 0, go down to its minimum, go up to its maximum, and then come back to 0 here, and then it's going to do the same thing again. So let's draw the graph. It'll look something like this, and we know that the maximum value of sine is 1 and the minimum value of sine is negative 1. So when we plug that into here, we see that our maximum value of velocity is going to be d omega, and our minimum value of velocity is going to be negative d omega. So these points here are going to have a height of negative d omega, and these points here are going to have a height of d omega. Now let's take a look at part C. Determine an expression for the kinetic energy of the system as a function of time t. We know that kinetic energy is simply 1/2 mv squared. And all we have to do is plug in the velocity function that we're given right here, but squared. We know that when we square something, the negative goes away. D squared, so we get 1/2 m d squared omega squared sine omega t squared, sine squared omega t. There we have it. And now let's find a expression for the potential energy U of the system as a function of time t. We know that the potential energy of a spring can be written as 1/2 kx squared, where x is the displacement from the equilibrium position, which we also have an equation for. So we'll have 1/2 k and then d cosine omega t squared, which will give you d squared cosine squared omega t. Here we go. Now part 3 asks us to use the equations from the previous parts to show that the rate of change of the total energy is 0. So the first thing we want to do here is just write the energy and then take the derivative after. We know that energy is 1/2 mv squared plus 1/2 kx squared. So energy in this case will be half md squared omega squared sine squared omega t plus the potential energy, alright, and then when we find dE dt, that's just going to be the derivative of the other side. Derivative of 1/2 md squared omega squared sine squared omega t is we're gonna keep all of these constants in the front, and then sine squared of omega t will give you 2 sine omega t times cosine omega t, and the 2 that we're given cancels out with this 1/2 right here. So we get md squared omega squared sine omega t cosine omega t. I ran out of space here. That says omega t plus the derivative of this here. We see that this squared and this 1/2 are going to cancel, so we'll get k d squared cosine omega t times sine omega t. Sorry, one of these is going to be negative. Let me just figure that out real quick. Derivative of cosine is negative sine. So this is going to be minus. And now we know that this is equal to 0, so we can just replace this here. This will give you 0, meaning that we can move 1 over to the other side in order to make both of them positive. Kd squared cosine omega t sine omega t is equal to md squared omega squared cosine omega t sine omega t. And from here we can see that some of our terms cancel out. We have the cosine, the sine, cosine, sine. We have d squared, and we're left with k is equal to m omega squared. And if we divide both sides by m, we'll get omega squared is equal to k over m, which we know to be true because this is one of the equations that we are taught in the oscillation unit. So therefore, the fact that we get omega squared equals k over m, which is a true equation, verifies our solution. Let's move on to the next parts. Alright, here we have a oscillating system with 2 springs, and here we're looking at the relationship between the mass of the clay that is put on top of this cart and the time it takes for an oscillation to occur squared. So as we can see here we're given a graph with the best fit line for that slope. And so we're looking for the k, the spring constant of each spring, because we have 2 springs here. So let's just write out our basic oscillation equations. We know that ma is equal to kx, therefore acceleration is k over mx. We know that acceleration is also equal to omega squared x, meaning that omega squared is going to be k over m. We know that omega is 2 pi over t. When you distribute the square, you'll get 4 pi squared over t squared is equal to K over M. And now from here we have a graph where we have T squared on top and mass of clay on the bottom. So let's replicate that here by flipping this K and this T squared. So we'll get T squared over mass of clay is equal to 4 pi squared over K. But one thing that I forgot to put in here is that this K is actually going to be 2K because we are given 2 springs. So yeah, that is a crucial part of our equation. As you can see here, we have a factor of 2 that can cancel out. And so the slope that we get here, T squared over mass of clay, is going to be equal to 2 pi squared over K. So 2 pi squared over K is equal to slope. Let's see what that is right here. As we can see, the graph rises approximately 0.75 and it runs approximately 1.5, meaning that the slope, we can approximate it to be around 1/2. There we go. Multiply this side by 2 and this side by K, you'll get K is equal to 4 pi squared. And let's take out our calculator in order to see what 4 pi squared would be. It gives us a value of somewhere around 39.47. So there you have it. Your K spring constant of each spring is going to be 39.47. Now let's move on to the last page. I'm going to erase all this here, but I'm going to write that our K is 39.47. I'm going to round that to 39.5. And now it's asking us to find the mass of the cart. So let's rewrite our equation. We know that the spring constant K is 39.5, and if we go back to the graph, we can see that when the mass of the clay is 0, meaning that when the mass of the entire system is just going to be the mass of the cart, the oscillation period squared is going to be roughly 1.5. So our T squared is 1.5. And so let's write out the equation. We have omega squared equals 2K over M. So then we get 4 pi squared over T squared equals 79 over M. 39.5 over 1.5 gets you 79 over M. When we simplify this, you'll get 1 over 1.5 is equal to 2 over M. And then this will give you, hold on a moment, let me recheck my calculations. Sorry, instead of 1.5 I meant to say 0.15, which is where the issue came in. So instead of 1.5 we're going to have 0.15, meaning that our mass is going to be 0.3 kilograms. There you have it. And now let's move on to the last part of the question. The experiment is repeated, but in a second set of trials, the cart is pulled back a distance d, where d is greater than little d. Describe any changes that will occur to the straight line on the graph in part D. So when our displacement is changed, this will not affect our period squared, because what does affect our period squared is our mass, our spring constant, and 4 pi squared, which does not change, meaning that the time it takes for one complete oscillation to change will not be affected, and obviously the mass of the clay will also not be affected, therefore meaning that the line will stay the same, and it will keep the same slope, and it will not look any different. Alright guys, that's all I have for you today. Thanks for watching. I hope this was able to help you learn AP Physics and how to solve this problem, and I'll see you guys next video.